Okay, and welcome back everyone. So in this video we're gonna play around in Excel and like we talked about in the previous problem, we added convective resistances in the mix. Okay, so in this Excel spreadsheet we're just gonna compute the overall rate of heat transfer right here, and we're gonna be varying the radius of insulation. R3 right here is the radius of insulation. We're gonna see how varying that is gonna impact our log mean. I mean, of course it's gonna impact your log mean area and the resistance, the resistance due to the conductivity of the insulation, the external convection, the external convective resistance, the total resistance, and as you can see in the equations on the right side, q dot is gonna be q dot is also gonna depend on the radius of insulation. Okay, so let's start. So okay, the resistance, the resistance due to the thermal conductivity of the pipe. So that's just going to be R2 minus R1. R2 is the outer radius of the pipe and R1 is the inner radius of the pipe. Divide that by the conductivity of pipe. And okay, so again, these are the numbers right here are not really important. What I'm trying to show here is as you guys will follow along, it'll make more sense what I'm trying to say. Oh, wait a second. I did not include area log mean, so sorry about that. So we need the log mean area first, as you can see in the formula here. The log mean area, good thing I have the equation for that as well. So that's just going to be 2 times pi times the axial length, which is 50 in my case, and multiply that by the difference in the radii, r3 minus r2 minus r1, and divide that by the natural logarithm r2 over r1. Okay, all right, pretty good. Okay, that looks about good. That looks good. Okay, that number makes intuitive sense. Okay, pretty good. Once again, r2 minus r1, 2 minus r1, divide that by the conductivity. All right, where's the conductivity of the pipe? Good. Divide that by the log mean area. So again, the thermal resistance due to the conductivity of the pipe, a very small number. A very small number because if you remember from the previous problem, our pipe was made out of copper. Copper, highly conductive. Good. Internal convection. Okay, we have the equation for the resistance due to the internal convection. So for this one, we're just going to be using the heat transfer coefficient on the inside. H sub I, heat transfer coefficient on the inside. What about the area? So that's just going to be the surface area of a cylinder on the inside of the pipe. And that's just going to be 2 pi times the inner radius. Multiply that by the axial length and we're good. Okay, 2 pi RL. Good. All right, again, a very small number. Why is that? And the reason for that is this really high heat transfer coefficient. The 10,000, that's a big number. All right, watts per meter square Kelvin. Good. All right, R3. So our R2 is 0.035. So the number that I'm going to start off with is going to be somewhere around 0.0355. So the thickness of your is just going to be R3 minus R2, which in this case is just going to be 0.0005 meters. And I think that's roughly 0.5 millimeters. Correct me in the comments if I'm wrong. Okay. Okay, the log mean area corresponding to this radius. Okay. And that's just going to be, once again, 2 times pi times the difference in the radius, R3. I'm varying R3. Keep in mind R2 is, I'm not varying R2, so that's going to be an absolute reference. Okay, I'm not varying R2. I'm only varying the outermost radius, R3. R3 divided by R2. Okay, I think, all right, 1 second. I think I might be missing, okay, yeah, I am missing the, I am missing the axial length here. The axial length, 50, and make that an absolute reference. Good. All right, the resistance due to the conductivity of the insulation. That's just going to be R3 minus R2. R3 minus R2 is going to be absolute reference once again. Divide that by the conductivity of the insulation, 0.04 right here. Good. Absolute reference that. And yeah, the log mean area. Pretty good. Okay. All right. So this number might seem small, but it's way bigger compared to this number. Okay, orders of magnitude bigger. External convection, 1 divided by the heat transfer coefficient. We're not varying the heat transfer coefficient, so that becomes absolute reference once again. And the outermost area, the outermost surface area, that's just going to be 2 pi times the outermost radius times the axial length. Again, we're not varying the axial length, so that's going to be an absolute reference once again. Good. All right. And this right here is going to be a sum. Okay, so I'm not varying these two resistances, so I'm just going to make them, oops, my bad. Maybe one day I'll learn how to format everything. So both of these numbers are going to be absolute references. Okay. And also we're going to add the resistances that we're actually varying, which are these two. Okay, that makes, all right, the numbers make sense. And now obviously the overall heat transfer, the overall rate of heat transfer is just going to be the temperature difference. We're not varying the temperatures. So yeah, guys, absolute reference. All right. Good. Okay, so now we know the rate of heat transfer at a outermost radius of 0.0355. And since we have a spreadsheet, now we can play around with some numbers. Let's say, how is this going to look like how is this going to look like at 0.036, for example? Again, everything should pop down. Let's see. Yeah, everything has looks like my spreadsheet works. So let's just keep adding numbers. Actually, all right. Now I'm just gonna select this one right here. Actually, all right. So the heat transfer, the rate of heat transfer is increasing actually, as you can see. And this is actually bad. This is actually bad. Think about it. You're adding more insulation. But the rate of heat transfer is actually going up. Okay, that's a very important point here. All right, that's a very important point from an engineering standpoint. All right, okay. Look at after 0.038. After 0.038, the outermost radius, the heat transfer rate actually starts to come down, as you guys can see here. Okay, it's starting to come down. So let's keep doing this for some. Oops. What did I do? My bad. Oops. All right, sorry about that. I mean, we can do this I just want to do this for more numbers. Okay, so now we have more numbers, and for your convenience, I've already added a chart. The chart plots the on the horizontal axis I have R3, the outermost radius, and on the vertical axis I have the rate of heat transfer. So you can see there's a stationary point, there's a maximum. So at a radius of 0.038, you get a maximum rate of heat transfer. So that right here is your critical radius. Okay, this value right here. Give me 1 second. Let's see if I can draw on this. Maybe not. So in this case, 0.038 is your critical radius, and you always want to be above. If you want to add insulation, the radius of the insulation should always be above the critical radius. Otherwise, you're gonna be increasing the rate of heat transfer. And why is that? Now we have to rationalize that. Why is that happening? You're adding more insulation, but your rate of heat transfer is also increasing. That's because as you add more insulation, the available area starts increasing. All right, guys, the available area starts increasing. And there's actually a very neat formula for the critical radius. So R critical the critical radius. I'm not going to go through the derivation here, okay? For that, I'm just going to refer the textbook. The critical radius is actually just your, if I remember correctly, it's just going to be the conductivity of the insulation divided by the heat transfer coefficient associated with the external convection. All right, so this is the exact analytical value. So if I were to write it here, the critical radius is going to be equal to the conductivity of insulation divided by the heat transfer coefficient on the outside. All right, so yeah guys, so this pretty much concludes our video. So yeah, this was a fun engineering exercise. We explored how varying the radius, keep in mind by varying the radius you're actually varying the thickness of insulation. How does that impact the rate of heat transfer? And we were able to visualize that pretty nice. So again, at the critical radius you're going to have a maximum rate of heat transfer. And why is that? Because you're providing more area. Okay, by providing more area you're actually lowering the thermal resistance. But you can also plot thermal resistance. So actually, before I conclude this video, I'll just add 2 more plots. So we're gonna have, let's see, okay, so I just want to plot the resistances versus the radius. Okay, so this right here is the, okay, oops, yeah, I'm just playing around with this. I have to be very careful, my bad. All right, so now I'm just gonna select data. All right, hopefully I'm not gonna mess this up. Edit that. On the x-axis I want everything below that. Pretty good. All right, what's also, I can give this a name. This is the resistance due to insulation, or insulation, and I'm gonna add 2 more. All right, this one's gonna be due to external convection, and in the horizontal values we're just gonna have the R3 as our radius. Okay, and all right, patience is a virtue that hopefully I won't run out of. All right, pretty good. And another one, a final one. All right. Oops. The final one is going to be total resistance. That's just going to be, okay. So again, this is going to go all the way down. Oops, my bad. This was supposed to be not here. Sorry about that. We're both learning. And on the x-axis, all right, on the vertical, we're just gonna have, okay, how am I gonna do this? So let's see if I can just finesse this, because I have all that stuff in the way. That's gonna be in the J block, $J9, all the way till $J$38. All right, I just had to finesse that because it's kind of hard to move this chart. Okay, so again, this doesn't make a lot of sense right now. So just to add axes, okay, we need to add axes, and we need to add our legend. So the blue one is the resistance due to insulation, and as you keep adding more insulation, the resistance due to insulation, the conductive resistance, is going to increase. But the external convection, the resistance due to external convection is going down, and there's going to be a minimum value. So let me just format this real quick for you guys so you guys can see. R3, Oops, sorry about that. All right. Patience is a virtue once again. R3. And this is on the vertical axis I have the resistance. I'm not gonna add the units right here because I'm just demonstrating. All right, I'm not gonna show this to my boss. This is not a good example. Again, guys, this is not a good example of data visualization. Don't follow my lead on this. All right. Again, what am I doing? All right, pretty good. My bad. Said that pretty soon. All right, pretty good. All right. So just let me see if I can adjust these axes. The numerals are gonna go from, instead of 0, I'm just gonna start off at 0.03. All right, 0.03, actually 0.034 to be exact. Yeah, as you guys can see, the total resistance is actually gonna reach a minimum somewhere around 0.038. And yeah, at the critical radius you're gonna have a minimum for the total resistance. Okay, so yeah guys, so now we know how the overall rate of heat transfer varies. Okay, we know how the overall rate of heat transfer is gonna vary, and we were able to get a good explanation for that by visualizing how the thermal resistance, both the resistance due to the conductivity, the blue one, the resistance due to external convection, and the total resistance. We saw how those depend on the outermost radius. So yeah guys, thank you so much for watching, and I hope you guys enjoyed this engineering exercise. All right, thank you very much.